We are live also on YouTube now, so perfect.
Nice. You're quite the pro at this, Michele.
Well, I had a few some
We are
experience.
live also on YouTube now, so perfect. Nice. You're quite the pro at this, Michele.
Okay, I have to close just.
Well,
Perfect. I I don't have to have a. I need to be careful. Close it.
so are you hearing me okay? Because I'm getting an echo.
Now
My
the
end.
echo was because it was on YouTube and YouTube gets a bit delayed, right? And I had not uh taken the I had not muted the YouTube, so that's why.
Okay.
Now it should be fine.
I just admitted someone called Zoom user, so I don't
Hmm,
know who that was.
okay. I'll ask them to.
Is the Read AI meeting notes something that you started, Michele?
No,
Do you want to unadmit them? I don't know what it is.
yeah, I don't think that. Yeah, I don't. I think I'm gonna deny the request. Sorry, that's probably in AI transcription.
Right.
Okay, so 1 second. So monitoring a bit with so many people, right? Um,
Right. You're a third of the way there. Um, should we give it a few more minutes or go ahead and start?
maybe just a couple of minutes, I think. Probably.
Okay. Give most everybody in.
It's okay if you want to start at 103. I don't have, I'm gonna leave plenty of time for questions, so I'm not, you know, worried about the time. So
Thank you, Francesca. We may take you up on that. So
yeah, people are still coming in, and takes
a lot of people we recognize, so it's so cool. Michele, do you want to make Gary co-host so he can help you?
Yes, I thought he was already. Yes, he is.
He's already co-host. Okay.
Also making Jennifer. She's gonna help.
Okay. All right. So I'm going to stop admitting people and let y'all manage that part.
Perfect.
Okay. Hey, Michele, do you think it's okay if I go ahead and start?
Perfect.
Okay, great. Welcome, everyone. I am Kathy Enser, and I'm chair of Section U, the statistics section of AAAS. And I'd like to welcome you to the 2024-25 inaugural webinar series talk. Just a little reminder, the AAAS mission is to advance science, engineering, and innovation throughout the world for the benefit of all, advancing science, serving society, with a vision statement of a boldly inclusive, mobilized, and global scientific community that ignites, enables, and celebrates scientific excellence and science-informed decisions and actions. I encourage everyone who's not a member to consider joining AAAS and adding Section U to your membership if you are a member. Oops. The Section U Statistics Leaderships. So again, I am the new chair of the section, and Karen Cafadar is the secretary. Jose Dupuy is our council member. Early career representative is Gary Gopalan. Nominations and Leadership Development Chair, David Banks. The non-academic representative is David Corliss. The Membership Engagement Chair is Michele Guindani. Members at large, Key Long and Jennifer Clark. And I have to say, we formed as a group in early spring, and it's been a really active and vibrant activity. And we also thank the leadership of last year, as they really set us up well for progress this year. I'd like to take a moment for just a very special thank you to our Section U Statistics Webinar Subcommittee, who worked so hard to bring this webinar to you. And it's just been an impressive effort. And Michele, many, many thanks to you, and Gary and Jennifer. Just an excellent effort on your part, and our community thanks you. So it's with great pleasure to bring forward our first speaker for this webinar series, the well-known Dr. Francesca Dominici. Dr. Dominici is a data scientist whose pioneering scientific contributions have advanced public health research around the globe. Her life's work has focused broadly on developing and advancing methods for the analysis of large heterogeneous data sets to identify and understand the health impacts of environmental threats and inform policy. Dr. Dominici received her BS in statistics from University La Sapienza in Rome, Italy, and her PhD in statistics from the University of Padua in Italy. She began her statistics academic career at the Bloomberg School of Public Health at Johns Hopkins and moved in 2009 to the Harvard T.H. Chan School of Public Health as a tenured professor of biostatistics. At Harvard, she was also appointed Associate Dean of Information Technology in 2011 and Senior Associate Dean for Research in 2013. She is currently the Director of the Harvard Data Science Initiative, and Dr. Dominici was elected to the National Academy of Medicine in 2018. Dr. Dominici is also the founder and lead PI for the National Studies on Air Pollution and Health Group, which is a group of faculty, research scientists, postdoctoral fellows, graduate students, and college students studying data science methodologies in the context of climate change, environmental impacts on health outcomes, and regulatory policy. The group has over 100 members and includes 25 principal investigators and faculty over 12 institutions. She is also one of the lead PIs for the BUSPHSHPH Climate Change and Health Research Coordinating Center, CAFE. The CAFE is a 3-year cooperative agreement with the National Institutes of Health, a critical component of the NIH Climate Change and Health Initiative to manage and support ongoing climate change and health research and capacity building efforts. It's our distinct honor of the AAAS Section U Statistics to host Dr. Dominici as our inaugural 2024-25 webinar series speaker. And with that, I'll turn it over to Francesca.
Great. Thank you, Kathy. Let me see, I'm gonna share my screen. Thank you for the lovely introduction. Thank to you and Michele for inviting me, and it's really my pleasure to address this audience. So what I'm planning to do is I will be speaking for approximately, I would say 35-40 minutes. I found very hard to be concentrated for longer seminar, and then I'll be delighted to take any question. What I do, I mean, just because we have all been living the Zoom reality now for so long, I'll go a little bit easier and slower. Just because this is my experience when I attend seminars, which is over, packed 1 hour at fast speed, it's very hard to follow. So,
Francesca, let me jump in just a second and tell everyone that they can put questions, the Q&A questions in the Q&A, and we'll take them at the end of Francesca's talk. So
perfect. Exactly. That's great. So, here is what I'm going to talk about, a little bit of a higher level, being a Zoom talk, but I want to talk about the new EPA rule on soot pollution, which is, I think, a very successful step forward in regulating fine particulate matter. I'll tell you more about this rule, and is also extremely important to regulate emission of greenhouse gases, and so it's going to advance also our advanced policy with respect to climate change regulation. I'll tell you the role of my lab, really the standard role of my lab at the general research of many people that have been interacted with me in the last few years, that is really at the intersection of AI and data science to influence this decision. The role of the media in taking all of this, and then the role of data science more generally in the field of climate change and sustainability. So first of all, excellent news. This was really something that I personally have been working for, oh my God, like over 20 years, which was to really do the best possible data science to influence this regulation. So last February 7, 2024, the U.S. Environmental Agency announced a final rule to strengthen the national ambient air quality standard for fine particulate matter. So they decided to lower the annual average from 12 microgram per cubic meter to 9 microgram per cubic meter. You see here the article of the New York Times. The Biden administration moves to tighten limits on deadly air pollution. And then a screenshot of the EPA of their cost-benefit analysis. And you see that by making the safety standard for fine particulate pollution more stringent has a benefit of between 22 billion to 46 billion. And so in terms of being a statistician and a data scientist, what has been my goal has been to really thinking first of what is the role, what type of policy decision do we want to impact, and how can we do the best possible statistics and data science and now AI to impact this role. So this is the role, and then I'm going to give you the general overview and simplified, of course, of how my lab and many of the colleagues, this is not only my work, but generally there is an extended network that has been able to impact this decision. So in this talk, I'll tell you a little bit about two of the, I would say, foundational paper that we published last year in April 2023, a paper in the New England Journal of Medicine that really provide, I would say, really a rigorous evidence of what's going to be the public health benefit and the number of lives saved if the EPA was going to have a quality standard more stringent. A more recent paper in November 2023 this was led by Lucas Henneman at George Mason University, with also my former postdoctoral fellow, now full professor at Brown, Corey Ziegler, to show the mortality risk that is resulting from coal electricity generation. Then what happened this year is a COP28, for the first time, there was an health date has been recognized that the climate crisis is indeed a health crisis. And I think I would say, this was a mix also of a lucky day in terms that Senator Kerry at the opening of COP28 mentioned and explicitly talked about our paper in Science as one of the strongest evidence that we need to face down fossil fuel combustion. I didn't know, I was in the audience, and you can see here I was jumping up and down, extremely happy for the fact that he pointed out this to such a important audience as a COP28 in Dubai. And then, as I mentioned, in February 2024, finally, we had the Biden administration taking this very important step in leading to more stringent national ambient air quality standard, which means cleaner air, life saved, and less greenhouse gas emission. So this is, I would say, the general overview of this talk and what I'm going to tell you about it. So first of all, I mean, I'm sure many of you knows, but just in case you don't, fine particulate matter, where does it come from and how it can affect me? We have several sources of fine particulate matter. Fine particulate matter can come from traffic, construction, industry, forest fires, residential burning, agricultural burning. And there is a very extensively documented now what are the effects of PM 2.5 on adverse health outcome. There are thousands and thousands of studies and papers. It can affect pretty much everything now. I mean, it can affect your respiratory system. You can affect your cardiovascular system. Now there is evidence of neurological effect and, of course, increased mortality risk. The other thing to always keep in mind that sometimes this is lost is that by regulating fine particulate matter, we are also making an enormous amount of progress in regulating CO2. So by passing a law that regulates PM 2.5, we are also having a law that's going to regulate carbon CO2 and greenhouse gases emission. To give you an example, this is not my data. This comes from a website called Climate Trace. It's a website that quantify the carbon emission of different activities. So in the United States, so this is in North America, right? You have to think that 24%, 50% of greenhouse gases emission are due of actually CO2 emission are due to fossil fuel operation. 24% to transportation, and 30% of power. These are exactly the same sources of PM 2.5. So if you look at where are the CO2 emission by sources, are pretty much in the same areas where there are PM 2.5. So this is just to say very high level as some background information that the sources that lead to PM 2.5 are the same sources that lead to CO2 emissions. So if you pass laws about PM 2.5, you are automatically regulating CO2 emission. Now, we have a long history in the United States where actually, because of the Clean Air Act that requires the EPA to review all of the empirical evidence of adverse health effect of pollution, I think is a classical example where data and data science have provided evidence that have been led to policy change, that have led to cleaner air, and they have been led to less greenhouse gases emission. If you see on this plot on the left, is actually really, I would say, a very good story that over the last, from the 1990s to 2015, because of this way of informing policy using data and data science, the level of pollution have been going down over time, and we definitely have less polluted air. Now, I've been focused for many, many years in try to provide the best possible evidence to address this specific question, which is ambient exposure to fine particulate matter below what were before the National Ambient Air Quality Standard, which were originally set at 12 microgram per cubic meter, associated with an increased mortality risk? So this is a question of trillions of dollars. As I mentioned before, the Clean Air Act benefits are ranging from 1.9 trillion to 3.8 trillion in 2020 and 2.5 to 5 trillion in 2030. So whatever is a rule that has, a tremendous amount of potential benefit, there is also, as you can imagine, a highly controversial rule because of the interest of the automobile industry and the fossil fuel. Now, one of the things I always say as a data scientist that there is not data science without data. and so I've been devoting a lot of my attention and many, many years of work into building together large data platforms that link together information about exposure to environmental agents, risk factors, the urban environment, and how they affect the health outcome. And so we are now really thinking toward developing artificial intelligence, including generative AI, to do causal reasoning for policy decision. So we have assembled all of the data on exposure to the environmental contaminant. We also have the data on power plants. I'm just going to mention a little more. We have assembled data on the fracking wells, on traffic. We link this data to health outcome. We have the 100% Medicare and Medicaid data. And then we add data on confounders. These mostly come from the census data. So these tend to be area level potential confounders on socioeconomic factors. But the general idea is take all of the possible data. These are heterogeneous data sources of everything that can affect the environment, all the possible data on the health, and all the possible data on the confounders. So what the study I'm going to focus will be the study on Medicare data. The Medicare data include over 67 million individuals. They are followed longitudinally over time. This is an open cohort because every year, everyone in the United States, or the great majority in the United States that turn 65 years old, get into Medicare, so are in our database. We have all-cause mortality and cost-specific hospitalization at individual level. We also have individual level information on date of death, age of entry, year of entry, sex, race, whether are eligible for Medicaid, which is a proxy for the lower socioeconomic status, and then we have a zip code of residence and other covariates. So one important element of now this field of machine learning and artificial intelligence, which is continuing to develop. By the way, there is an entire society here on what we call a geospatial AI. And so this field is growing and growing, which is basically developing machine learning artificial intelligence model to allow and measure and interrogate spatial temporal data. In our context, what this map shows is where we measure PM2.5 in the United States. These are EPA monitors. You can see there that there are several thousands of monitors, but there are areas where there are very few monitors, right? And so this is work that was originally led by my colleague here at Harvard, Joel Schwartz. And then this is now an entire field, which very candidly, I'm not the expert, but it is an entire field of developing ensemble learning and machine learning, or now I call it geospatial AI. What they do, they combine information from chemical transport models. They train this model by the output of chemical transport model and also by land use terms, by meteorological variable. They're supplemented by satellite measurement, and they are further trained by monitor data. Then they are analyzed what we call ensemble learning. And the bottom line is this model, they are so complex, so rich, so flexible, they allow us to estimate at 1 kilometer grid the level of PM2.5 that we are exposed with high level of accuracy. I can say that there are hours and entire workshop, and probably now I will call it maybe, I don't know, 200, at least 200 research papers. They're actually just developing machine learning models to do exactly this, to estimate exposure to environmental contaminant. Back a few years ago, we used one of these models to be able to basically fill the missing data and fill the gaps in terms of understanding exposure to PM2.5 in areas that were not monitored very well. So there is more work going on, including doing a hyperlocal estimates of components of PM2.5. This map shows, for example, up to 100 meters resolution of exposure to elemental carbon. And so just to give you a sense of how sophisticated we can be now, because we have almost unlimited computational power and an enormous capability to fit this highly complex machine learning model. So in 2017, we had this first landmark paper where we link exposure to air pollution and PM2.5 and mortality in the Medicare population. This was the first big, I will call it Medicare paper. The goal was to see whether or not we have an increased mortality risk, a level of PM2.5, even below at that time, the National Ambient Air Quality Standard. If you look, we had a large study population, over 32 million individuals and 247 person years for people that were breathing a level of PM2.5 below 12 microgram per cubic meter. And the goal to see whether in this cohort, we will see an increase in mortality risk, because by law, if we can quantify that there is and show that there is an increase in mortality risk, even a level below 12, where 12 were at that time considered to be safe, by law, they will require to revise the National Ambient Air Quality Standard. When we conducted this analysis in 2017, we analyzed this data using very simple, I would say, traditional methods. This was from a statistical viewpoint, we fit Cox proportional hazard model, then we approximate this Cox proportional hazard model with Poisson models. We adjust for confounder by using additional linear term. So I will call it basically the bread and butter of stat and air pollution epidemiology. And what we found was that for 10 units increase in PM 2.5, was associated with a 7.3% increase in all-cause mortality that was statistically significant. So the horizontal line is the mortality risk for the overall population. And then we also did like a stratified analysis where we also estimated the mortality risk associated with a 10 units increase in fine particulate matter for the Black American, for the Asian American, for people that are also eligible on Medicaid. And you see that we found at that time, this was pre-COVID, a higher risk of mortality, actually three times higher risk of mortality of PM 2.5 among Black American than for the whole population. At that time, this was during the Trump administration, 2017. Of course, this paper had a lot of media attention. It was received very well from some people and not very well from other people. So these were the coverage of the New York Times, the coverage of NPR, Senator Cory Booker. There is actually a clip that you can see on my website that he was extremely concerned about the results of our study, especially because, you know, he was very vocal about the high risk for the Black American in the United States. Now, then we had COVID, and COVID, as you can imagine, as you remember, you know, changed pretty much everything. And at that time, when, you know, because we had the entire data platform, and as the COVID exploded, I had the intuition, which actually I don't think was a particularly like groundbreaking ideas, but basically what I thought was to see as whether exposure to fine particulate matter was increasing the mortality risk after you're getting COVID. And the idea from I would say, a clinical viewpoint makes a lot of sense because COVID-19 was clearly a respiratory infection. And their intuition was if you are a respiratory infection, you have COVID, in addition, you are breathing PM 2.5, your mortality risk would be even worse. So we published a paper in Science Advance. This was a very straightforward, by you know, clearly an oversimplistic analysis, but did show that there was an association, and they had also, you know, really attract a lot of attention. The reason why I want to mention this is because, as you will see during the talk, these analyses really also had an impact on the policy decision. Of course, because of the highly politicized nature of both air quality regulation in the US and COVID, this is just one example of, I would say, the political pressure that I had to endure as we were publishing the study. So the Washington Post reported a Harvard study tying coronavirus death rates to pollution is causing an uproar in Washington. They say the stakes are high because the study tentative findings could prove enormously consequential for both the pandemic impact and the global debate over carbon air pollution. I had Michael Bloomberg on my side, other people not on my side. And again, you know, it wasn't really taking a side. It was just showing something that, in my opinion, make perfect sense from a clinical standpoint. And so, you know, it was really hard to do science at that time. And so here, you know, this is Summers that the research and the ensuing criticism highlights how fraught it has become to conduct science during an health crisis. So this is also, just to say, this was work also collaborated by former PhD student. Zhao is now a faculty member at Columbia, and Rachel, who is also a colleague, a faculty member here at Harvard. And these were the coverage of the New York Times. Now, since then, so many things have changed. And one of the biggest criticism of the research, not only on mine, of other people, was really the degree to which we would show there was a causal link between exposure to air pollution and mortality, or exposure to air pollution and increased mortality risk due to COVID. So since then, there's been, the last couple of years, a new committee of the National Academy of Science that reviewed whether or not what is the role of causal inference in regulatory policy. I should have said that during the Trump administration, regarding the work that we published, the Trump administration declined to pass and review the suit rule. We then actually the Biden administration just last February, finally, as I said at the beginning of the talk, decided to pass a more stringent law. So you can see that there is a really very informative, balanced report of the National Academy of Medicine or what is the role, not absolutely only by my work, but in general, what is the role of causal inference from when you're trying to have a multidisciplinary evidence base for national ambient air quality standards. I want to give you a 2 minutes, general idea of causal inference in this field. And what are I will say, the plus and minus, right? So I show you that in the first paper in the New England Journal of Medicine, we use a standard regression approach. And so generally, the general criticism of this field of research was that by fitting a regression model, we could not assess evidence for causality. Now, the gold standard of evidence for causality, as many of you know, will be to run a randomized experiment. That's why, by the virtue of randomization, you can completely control for measure and measure confounding. Unfortunately, in air pollution research, in environmental research, you cannot conduct a randomized experiment. So what you're stuck is with analysis of observational study. But the good news is that there is an entire, very well-established field of causal inference. I'm just showing you a screenshot of one of many, many books. For example, The Causal Inference, a book by Ido Imbens and Don Rubin. Ido Imbens and colleagues won the Nobel Prize in Economics a couple of years ago. And the idea of causal inference for the analysis of observational study is basically to take observational data and try to approximate the randomized experiment. So I'm going to give you a toy example with this figure, right? So let's say that you have only 2 locations in the United States, right? Just think as simple as possible. There is a location in Steubenville, Ohio, which has a higher level of fine particulate matter. And then there is another location in the United States that is Portage, Wisconsin, that has a low level of fine particulate matter, okay? Then in Steubenville, Ohio, let's hypothesize that I have a data on a woman, her name is Jane, right? So let's say that Jane is a woman which is 52 years old. Jane has a low education, right? She has a low socioeconomic status. Let's suppose that Jane doesn't smoke. And let's say I have some information about Jane, about her characteristics, right? So I know that Jane was unfortunately bred, was exposed to a high level of pollution. And I have some idea of her characteristics. And I know that Jane died at 72 years old, right? So now what I need to do from a causal inference perspective, I need to figure out what would have been the age of death of Jane if the same Jane would have lived in Portage, Wisconsin. And that's called the counterfactual. Now, of course, we will never be able to know that. But if you have a large observational data, what you can do, you can go to Portage, Wisconsin, and try to identify this subset called A prime, which will be all of, I would say, hypothetical twin sister of Jane. So I can go to Portage, I can identify all of the women. They have the same age as Jane. They have low socioeconomic status. That's why they're all green. They don't smoke. They have very similar characteristics. And let's say that among these women, the average age of death, let's say, was 80, right? So if Jane died at 72 years old, and if her twin sister in Portage died at 80 years old, it means that living in Portage and breathing cleaner air will give you 8 extra years of life. That is the fundamental, I would say, 101 idea of matching. For every individual that breathes a certain level of air pollution, we are going to find all of its matches in an area that breathes less level of pollution. Now, we can do that now for every single Medicare enrollee going over 67 million of individuals. And that's what it means to do causal inference for the analysis of observational data. That's exactly what we did. We went back to the Medicare data and we reanalyzed the Medicare data with state-of-the-art method for causal inference and led this work, which was led by Zhao Wu and Danielle Brown, which we published in Science Advance. And basically, we were able, by doing matching is when I say I found Jane in Steubenville, and I found their twin sister in Portage, Wisconsin. That is exactly what we mean by matching. And by matching, what we do is in the match set, we can eliminate the correlation between any potential confounders and PM 2.5. So the red dots is what are the correlation between any potential confounders and PM 2.5 in the original cohort. And that's the green dots is what will be the correlation after we do the matching. And you see that if the correlation is all below 0.1, it means that we are approximating a randomized experiment pretty well, because basically we don't have any remaining confounding between the measured confounder and the level of PM 2.5. So we redid all of the analysis, both going back to traditional methods and methods for causal inference. And the bottom line is when you're looking at the mortality risk associated with exposure of PM 2.5 for the entire cohort, both traditional methods and methods for causal inference give exactly the same results or very similar results. When we focus on the cohort of people that are exposed to level below 12 microgram per cubic meter, we see actually that these mortality risks are higher. We do see that the methods for causal inference provide a little lower estimates, but still these estimates are positive and statistically significant. In fact, we found that lowering their quality standard from 12 microgram per cubic meter to 10 will save over 140,000 lives in 1 decade. So we estimate the entire exposure response curve using methods for causal inference and showing that indeed, if you are declining and lowering the level of PM 2.5, you are saving life. And then we published a second paper more recently, again, using methods for causal inference, where we wanted to inform directly the Environmental Protection Agency and say how many lives you're gonna save if you're gonna lower the National Ambient Air Quality Standard to 10, to 9, and to 8, and also separately for the Black American with high income or lower income, and for White American with higher income and low income. These are enormous databases. Now we are dealing with 623 million observation. So back in, I would say, last year, this was really an important landmark paper because basically if you see this figure, which was the one that directly informed the new rule, showed that for different strata of the population, so the blue are the Black American, the orange are the White American, if the EPA were to lower the National Ambient Air Quality Standard from 12 to 11 or 12 to 10 or 12 to 9 or 12 to 8, that would be the reduction in mortality risk that we were going to see. And you see that it will be all statistically significant, and we will benefit people, Black American and White American with lower socioeconomic status than White American with higher income. So this was extremely important, as I said, in informing this new rule. Now, the other thing I want to mention before I conclude my talk, the other really important paper, which was published in Science last November, as I said, this was led by Lucas Henneman, George Mason, and Corey Ziegler, now at Brown School of Public Health, where I had the privilege of really working with them to link PM 2.5 directly coming from coal-fired power plants to mortality data in the Medicare and find two important results. One is that the mortality risk from exposure to coal-fired power plants is twice as large as the mortality risk from all sources from PM2.5. But importantly, we were able to quantify the excess number of deaths associated with every single coal-fired power plants in the United States. So on the bottom, these are all the coal-fired power plants in the United States. The darker dots are the ones that have a higher amount of emission. And then in the paper, you will see here, I'm just showing for the coal-fired power plant in the Midwest East, we were able to quantify the excess number of deaths attributable with each coal-fired power plants by different years, right? So for example, these coal-fired power plants in the Muskegon River in Ohio is the one that leads to the largest number of extra deaths, followed by one of Gibson, Indiana. If you go to a paper, there is actually a interface, an app that you can link and click of every single coal-fired power plants and look at their emission and their mortality risk. The other very important investigation, and I would say findings of this paper, is that we were able to evaluate whether or not specific strategy on coal-fired power plants were working. And so I'm just going to show you a classical example. On this coal-fired power plant, Gibson, Indiana, this plot shows the excess number of deaths over time. And you see that these, actually, sorry, for the Gibson, this was in the star was the day where this facility was shut down. And you can see, as expected, as soon as this facility was shut down, the attributable number of deaths dropped dramatically. And then in the Muskegon River, actually, I'm sorry, I've actually confused. Let me start again. This star is the date where in this power plant, they install a scrubber. And so you can see that by installing a scrubber, which takes out the toxic part of the PM2.5, the number of deaths dropped, right? So this saying that even if you don't shut down the coal-fired power plants, but if you install scrubber, the toxicity of the emission from that power plant goes down pretty quickly. When for the Muskegon River, this dot tell us when this Muskegon River unit was shut down, and of course the number of deaths also were facing down pretty quickly. So going back, this is how I am putting some of the pieces together. By no means the National Ambient Air Quality Standard was only revised because only of my work, but I wanted to give you an idea of two of the landmark paper that I think played an important role is in this decision. And I wanted to give you a little bit of a sense of what is behind in terms of the data, in terms of the database, in terms of the machine learning, in terms of the traditional statistical method, in terms of the causal inference statistical method, as well as the pushback of the different interest party and the different pieces of the puzzle, including the investigation with COVID. I want to conclude by just saying that the future, there is a really interesting and so many opportunity ahead in terms of the intersection of using artificial intelligence and data science for a future that is more sustainable and for environmental policy. So number one, my lab is leading a lot of the research on thinking about causal reasoning artificial intelligence model to impact air quality and greenhouse gases regulation. There is a lot of work, what we call climate smart public health system that can use reinforcement learning to inform cities, for example, on how to combat climate-related crisis. For example, we're going to face a tremendous heat waves in the northeast part of the United States starting tomorrow. There is an opportunity to deploy tools for artificial intelligence to measure and report the environmental and social governance of the tech sector. And then there is AI and generative AI that could be leveraged to basically have a better use of our resources. I'm going to stop here 15 minutes before the clock because I would love to have questions and engage in a discussion. Thank you very much for your attention.
Thank you, Francesca, for first of all, for all of your work on behalf of the world. So I don't know if any y'all are able to clap, but I know the audience is really appreciative. We do have a couple of questions, so let's go ahead and go to those. I guess, Michele, I'm just going to read the question. Would that be the right way to go?
Yes, or we can ask to unmute if recognize, of course, the person. So,
okay. Ann Taylor, do you want to unmute and ask your question?
Sure. Thank you. I'm just curious, with all the talk lately about microplastics and what size they are and whether they fall in the category of these same particles or whether they're a completely different class, whether there's any overlap there in those risks. Thanks.
It's a good question. To be candid with you, I don't know. There is so much research, which I'm not particularly expert. So yeah, I don't know the degree to which a fine particulate matter is capturing microplastic. I don't think to a big extent, but to be honest with you, I'm not particularly ready to address question with adequate scientific knowledge. But it's an excellent question. It's something to look into it.
Thank you. Tom Bellin, do you want to unmute and ask your question?
Yeah, sure. Francesca, Tom Bellin here. Thank you so much. Great to be with you virtually and echoing the praise for the talk. And I really appreciated the discussion of the methods. My question was early in the talk, there was a table of costs and benefits associated with the new rule, and the costs I noticed, I'm trying to remember which, the benefits were calculated, I believe, with a 3% real discount rate, and the costs were calculated with a 7% interest rate. And I was just wondering if you could explain how those interest rates contributed to the estimates and what was the motivation for using different interest rates for the different parts of that calculation?
Yeah, great question. And this is the second answer where my answer is going to be, I don't know. So first of all, let me say that this cost benefit analysis is done by the Environmental Protection Agency. Now, why they use, I don't know why they use a 3% versus 7%, but what I do know is that there is absolutely no question that the benefit by far outweigh the cost. Of course, this number, I don't even know what they really means, but they multiple analysis and multiple group, even outside the EPA, have done this cost benefit analysis. So the benefit by great deal outweigh the cost. And the other thing to keep in mind, Tom, is that when they do this cost benefit analysis, the benefit are actually a big underestimate. And let me tell you why. Because when they calculate the benefit and the cost by only looking at PM 2.5. However, when they pass a rule, for example, when they're going to pass a rule for having more stringent national meter quality standard for PM 2.5, that is going to impact automatically also other pollutants and other greenhouse gases emission, right? So the cost of implementing the rule will be the same, but the benefit will be higher because it's not all there, by implementing a rule and by cutting out traffic and by cutting down coal-fired power plants, you're not only reducing PM 2.5, but you are reducing on many other pollutants that are caused by these sources and therefore, improving lives. So I would say this, I don't have the insight of how these cost-benefit calculation are done, but I'm pretty confident that wherever you look at it, the benefits are by far superior than the cost.
Thank you, Francesca. Karen, let's jump over to you with your question. If you could
thank
unmute and
you.
ask it. Thank you.
Yeah. Thank you, Francesca. That was really interesting and I learned a lot. And I'm so glad to see it's getting so much media attention. Is there any way to ensure that subsequent administrations will not relax the environmental policies enacted by the current administration? And also, in view of the enormous effects of industrial pollution and air travel on PM levels and climate, how much of an impact do you think the replacement of personal gas-powered vehicles and associated production by EVs would have, which also themselves would involve production costs?
Yeah, these are all excellent questions. And I think you are overestimating my ability to figure out what's going to happen in the future. So, so first of all, I mean, again, my first answer is I don't know what from a legal viewpoint would be the ability of the next administration to reverse the PM 2.5 rule of the current administration. To my knowledge, it's going to be really, really hard because it's a federal rule. But having said so, this is about environmental law and policy, which is by far outside my expertise. So that doesn't mean that many things will be thrown out to try to relax it or like different loophole. Of course, will all depends on what would be the next administration. One thing that's been though, because I've been doing this work for now 25 years, I went through multiple administrations, and so my philosophy in addressing your question is the goal is to keep building the best possible data and the best possible tools and keep working, even regardless of what the current administration is going to be, because the politics and the ideas change, and as we've seen, the science and the data stay, right? And so, for example, when we published the paper in New England Journal of Medicine 2017, which was during the Trump administration, at that time, even though it was rigorous analysis, it did not lead to a change of the policy, right? Because of the political thinking. But then when the administration changed, that was still there, right? That they could rely on it, right? So my goal is to continue to do the best possible science, not to be influenced by the administration, knowing that this is a long-term game and science stay, different political administration and political opinion change. And then in terms of so there is a study that we are conducting on identifying whether or not the transition from completely EV vehicles, what's going to be the cost and benefit analysis of that? Because I had exactly the same question. So we are literally working on it right now. And it's not clear to me that transitioning away from diesel and gasoline and then relying 100% of electricity, it's actually is going to be a more sustainable future, considering that in the United States, there are entire regions in the United States, they cannot get enough electricity from renewable sources. So the idea that by it's not that we can rely on solar and wind and other completely renewable sources to offset the additional demand in electricity that we will need if all of the cars will be electric. But we haven't finished the careful analysis, because as you can imagine, it's not easy, but we are working on it. But that's what I mean by bringing together the best possible data, because even if we think that we're doing the right thing, we might not doing the right thing, and only the data and the science can tell us that.
Great. Thank you very much.
So, Francesca, again, I love your philosophy in terms of how you approach this critical science. We have a couple of Gavin McKay and Jesse St. John both in the Q&A. Gavin asked how undergraduates could get involved, and Jesse asked how she could apply data science methods in general and get started in the climate space. Do you have any words of wisdom for young people wanting to contribute in this area?
Yeah, I mean, I think that if you are, you know, at any stage of your career, especially if you're undergraduate, I mean, of course, I'm completely biased here, but more data science education you get right now, better it is for you, and can be data science, it can be computer science, or can be statistics. You know, doesn't really matter when you are an undergraduate. The goal is to learn how much about this technical field. And then you don't need to worry about data science in climate, because if you learn all of the skill about the coding and all of the concept about statistics and computer science that you need to have, then you can apply to everywhere. And so, you know, if you had a major in data science or a master in data science, then it will be very easy to apply these skills to address the type of question and problem that we discuss. So get as much data science education as you can.
Samir Deshpande, not sure if you're on, would you like to unmute and ask your question?
Great. Thanks so much, Francesca, for a really lovely talk. It seemed like an important part of the modeling pipeline was imputing those PM 2.5 concentrations at sites where you don't have the monitors.
Yep.
And I'm curious, could you share a little bit about how you actually validate those predictions? Because by definition, you don't have a measurement there. And maybe related to that is, how does the uncertainty about those sort of propagate down to your causal estimates?
Yeah, no, again, these are really important questions. And these are actually the most, I would say, exciting area of research that I think the community and my lab is also working, and happy to work with you on this if you want. But let me tell you where we are right now, right? So first of all, the model that we have used are only validated at the monitors, right? We don't have the gold standard where the monitors are not there. So they are not validated. The other thing is there is work now, and that's why actually there is this new Geo AI, and we are working on actually thinking about topological deep learning. That is a more sophisticated way to do the imputation, and potentially a better way to validate, including some additional monitors. So there are not the EPA monitors in area that are not monitored. And so it's, you know, it's a very, very active area of research. And that's why I said there are hundreds of people working on this, including the entire area of Geo AI. Now, in terms of the propagation, so there is still, I would say, a lot of research needs to be done to quantify the uncertainty. Now, we have done it in a couple of papers, and if you mail me, I'm happy to share it with you in terms of quantify the uncertainty. And then we have done also a couple of papers that have propagated the uncertainty. Propagating the uncertainty from the exposure prediction into the causal inference model is actually not easy, because if you're doing matching, and let's say you're doing matching with a propensity score,
Your estimate changes.
Exactly. So we have done a couple of papers that start to bring the ideas, but again, you know, much more needs to be done. So it's active, you know, and this is why this is an area that we are never really done, because every additional step is more research, but that's what research is about. So, but if you're interested in getting involved on this topic, please let me know, because it's a very exciting area of research.
Well, thank you so much.
Thank you, Samir. Francesca, we have lots of additional questions, but we're actually out of time. And so I would encourage our audience members that did not get to ask the questions to email you, if that's okay. Yeah.
I'll be delighted.
Be delighted. Okay. And I want to thank you again for everything you do on behalf of society, and you're such a stellar representative of the statistics profession, and we're so proud to call you our own. So thank you for being our inaugural speaker for our Section U webinar series, and thank you to the audience for joining in today. So.
Thank you. That's been a pleasure. Thank you for the great question. I hope to see many of you in person soon. Take care. Bye-bye.
Thank you.